memoization that we made in Mondrian. Most of you know what's Mondrian, that it's a visualization engine that it's developed Faro. It was initially developed in order to visualize software metrics. For example, Moose use Faro, use Mondrian in this way, but Mondrian has also been used to other goals. For example, it was used to visualize the behavior of robots or 3D visualization, such as clocks. The problem is that with each unpredictable use of Mondrian, a performance problem was found. This performance problem was solved with a memoization technique and different caches. But what is a memoization technique? A memoization is an optimization technique used to speed up an application by making calls, and in order to avoid the repetition of some calculations. It's a very simple idea in code. For example, we have here a variable that is a cache and is the value of the absolute bounds of this element. It's in the cache, so the cache is not here, we return the cache. It's not, we are going to calculate the absolute bounds for the element. But the use of memoization had some problems too. While these caches are used intensely in some kinds of visualizations, in others are not used. So in these other cases, they must be, they might be a source of slowdown. And also, the other problem is the legibility of the methods, because it's negatively affected. So the goal of this work are two. First, we identify this memoization, or in fact the use of caches as a cross-cutting concern, and then we are going to extract these caches, or the use of these caches, in modular and pluggable aspects. And we are going to do it using a custom AOP approach. Why custom AOP approach? Because we didn't find, we started with this, any AOP language for Faro. So, well, now it's fun. But we start with a rather naive solution. We try to use delegation in order to extract the caches. Enough graph element is the main class of Mondrian. It contains most of the caches that we extract. So we try to create a class. In this case, it's a kind of cache manager. So you can put things on the cache and then get it. But the problem of this kind of approach using delegation is really elegant, but it's too slow. In fact, really too slow for a visualization engine. So we tried another solution, and we thought that this kind of refactorization should be performed very carefully. We have some constraints. The first one, we think that all the caches should be identified as cross-cutting concerns and should be extracted. The most important constraint is that the performance must not be affected, because, well, the performance is very important in Mondrian. And finally, of course, the reliability must not be reduced. In fact, we think that the reliability must be improved. Well, how we identify the caches for people that know about AOP? We didn't use any aspect mining approach. It was easier than that. We only searched for all the places in which a cache variable was used, and we found 9 caches in the whole end-of graph element hierarchy of Mondrian, and we grouped all the fragment of code in which a cache was used based on the purpose of its use. So some fragment of code in which a cache variable is used to initialize and reset the cache. Others are used to get the cache value, and others are used to set the cache value. And when we identify the group, we also identify some code patterns in the way that these fragment of codes are implemented. In fact, we identify 5 code patterns that are lazy initialization, cache initialization, reset cache, return cache, and cache load. And these patterns are spread in the whole hierarchy of end-of graph element with different methods. Here there are only the main methods in which we found these code patterns. For example, what is the lazy initialization cache? Is in those situations in which it's not necessary to initialize the cache before it's actually needed. It's similar to the previous example that I showed. And it's, for example, I had a bounce cache. If the bounce cache is needed, so we are going to make the calculation for the bounce of an edge. If not, we are going to retrieve the variable value. In this case, if we are going to extract the cross-cutting concern related with the cache, we only need, in this method, the original code, that is self, shape, compute bounds for self. The other part of the code of this method, we are going to extract it in an aspect. Similar, reset cache is when we have to invalidate the content of the cache. And in this case, we have here 4 instances of the reset cache code pattern. Well, the variable is set to nil, or the variable is set to a new object. It depends on the structure of the cache, of course. So, the goal of our refactorization, as I said, is extract these cache, these code patterns that are related with the cache, but without changing the behavior of the program. We are going to do it, or we've done it. We did it with customized AOP mechanisms, and this customized AOP mechanism is based on injection code. We create kind of weaver that injects the code based on annotations. So, for each fragment of code, or for each method in which a fragment of code related with the cache variable was found, we extract the cache code and we annotate the method. The annotations are implemented with pragmas, and in this way we have the fragment have two parts. The first one is the pattern code name and then the cache name. For example, here, lazy initialization pattern is the code pattern that is going to generated and injected, and for what variable is going to be generated, it's here in this name of the pragma. So the injector works in this way. We can inject the code, and the injector looks for every method, looks for each method that has one or more annotations, and injects the code. And inversely, we can disinject the code generated. So for each annotation, the process that the injector follows is this one. First, for example, here in the method bounds, the cache concern had been extracted, so we only had the code related to the calculation of the bounds for this edge. And so the first step is to create a new method that has the same name that the original method, but with the prefix compute plus the name of the class. Then we are going to copy the original code into the new method. And finally, the injector replaces the code of the original method, but for the code generated by the injector. So in this case, it's almost the same code, but with the difference that now it's going here to the new generated method. And how we implement this? Well, the injector it's implemented in a very extensive way. We have a cache pattern that it's a kind of abstract class, so we can create for any new code pattern. We only have to create a class in order to know how to generate the code that is needed. And in fact, we create a generic AOP pattern that allows the injection of code before or after the execution of the method. We think that the contribution of this approach is twofold. The first one is that the reuse of code is improved. Of course, we are avoiding the repetition of code here, and also that the legibility is increased because now the cross-cutting concerns have been extracted, so we only have the original code in each of these methods in which memoization was used. Regarding the performance, we didn't have significant difference, so more or less are the same numbers before and after the refactorization. Well, to sum up, we identified 5 code patterns in the Mondrian hierarchy of the main class, and we create an injection mechanism to extract and reinject this code. We implemented it in an extensive way, and we did it without performance cost. Finally, I would like to thank to FAST, that is the Argentinian Foundation of Malta, because they are partially supporting my trip here. Thank you.
Is this available somewhere?
Yes, it's in Switzerland, but yes, it's in Switzerland. Yeah.
Did you integrate the environment to be aware of your framework? For example, the refactoring browser, if I rename the method shape or I don't remember the name, do you refactor also the compute or I don't know which are you then in one slide you show here, for example.
Yes.
If I then rename, because I rename bounds.
Yes.
I put Mariano bounds.
Yes.
Then could you map it to a compute MOH bounds?
Yes. The idea is this: you must follow this path. If you are going to execute Mondrian for some thing, so you are going to inject the caches that you are going to use. When you finish to use it, you should uninject it. So the injection mechanism is going to delete this method once that you uninjected. So the next time you are going to change this name, the injector is going to find this annotation and it's going to generate the correct code.
You also have an example where you caching for a method that takes arguments, where the result value depends on the arguments, but is actually always the same.
A method with arguments?
Yeah.
Yes, there are methods with arguments. I didn't put any on the slides because it's more complicated, but yes, we had to work a bit more with some of these samples because the refactoring was accomplished in a manual way, but well, the injector is automatic. Yes, but it works too with arguments.
Question. In slide 16, I guess, you have some performance analysis. What can you summarize from that? Are you better or analyzable on the first figure on the left?
Yes.
Why is this measured for the last?
For the last? We are not sure, but we run the test of Mondrian that are available in the current version of Mondrian. I think that were more than 10 times for each one. And we found that, yes, for a big number of nodes or edge, because a big number of nodes, this happened, but the code is the same. So we are not sure why, but we think that more or less the performance is the same because the final code is the same as the original one. So I'm not really sure why that difference.
That's strange.
Yes, it's strange.
Secure.
Yes, but the thing is that it's the very same code.
Yeah.